Bismillahirrahmanirrahim. Today's lecture is the second part of chapter 3, which we are discussing now. So, we today's topic is comparison of Otto cycle diesel and dual cycle, same inlet pressure and same compression ratio. Yesterday, we have in our last lecture, we have studied in detail regarding the cycles, constant volume cycle, constant pressure cycle, and then dual cycle. Now, once again, I quickly recap. First is the Otto cycle. On your x-axis, you have specific volume V. On your y-axis, you have pressure P. We have a TDC here, VDC here, atmospheric pressure. Now, in Otto cycle, piston is at TDC, 0.6, starts moving towards VDC, reaches 0.1, your intake stroke completed, intake valve is open at that moment. Now from 1 to 2, you have a compression stroke. Piston moves from VDC to TDC. From 2 to 3, we have heat input, or there is ignition or ignition and combustion going on. And from 3A, we have a maximum temperature, maximum pressure in a cycle. Now, from 3A to 4 is your power stroke or expansion stroke, in which you get the power at the crankshaft. From 3A, piston is at TDC, going towards at VDC. All valves are closed. At 4 to 5, we have exhaust blowdown, in which the exhaust gases leave the system, and this is also known as heat rejection. And from 5 to 6, we have exhaust stroke. Okay, this was the general Otto cycle which we have studied. Now, as far as diesel cycle, it's a constant pressure cycle. Now, process 6 to 1 is same, 1 to 2 is the same. Then we have from 2 to 3 C is the heat addition at constant pressure. From 3C to 4, we have power stroke, and then we have exhaust blowdown and exhaust stroke. In dual cycle, it's the combination of constant volume and constant pressure heat addition. In first part, we have constant volume addition, air at point 2. With point X, we have constant volume heat addition. And then from X to 3B, we have constant pressure heat addition. So from 3B to 4 is your power stroke, and 4 to 5 is exhaust blowdown, and 5 to 6 is your exhaust stroke. Now coming towards your temperature entropy diagram. 1 to 2 is the compression stroke, and from 2 to 3A is your Otto cycle, okay? And 3A to 4 is your power stroke, and 4 to 1 is your exhaust blowdown of exhaust stroke. In dual cycle, at point 2 to X, we have constant volume, and X to 3B, we have constant pressure, and 3B to 4, we have a power stroke. In diesel, we have from point 2 to 3C, constant pressure heat addition. So remember this TS diagram and the area under these points, 1 to 2, 3A and 4, 1 to 2 and X, X to 3B and 4, and 1 to 2, 2 to 3C and 4. Now, Otto cycle, diesel cycle, and dual cycle with the same inlet condition and the same compression ratio, we will get this type of a graph. The area under the process lines of TS coordinates is equal to the heat transfer. So the thermal efficiency can be compared for each cycle. Q out is the same process 4 to 1. Q in of each cycle is different. So Q out is the same. for the 4 to 1, but the Q in, the process from 2 to 3A or 3B or 3C, this is different. So thermal efficiency of Otto cycle is greater than thermal efficiency of a dual cycle, and thermal efficiency of a dual cycle is greater than thermal efficiency of a diesel cycle. Now, comparison of Otto, diesel, and dual cycle. The important variable factors which are used as the basis for the comparison of the cycles are compression ratio, peak pressure, heat addition, heat rejection, and the net work. In order to compare the performance of the Otto, diesel, dual combustion cycles, some of the variable factors must be fixed. So out of these 5 factors, we have to keep some of these variable factors fixed. So then we can compare these 3 cycles. In this session, a comparison of these 3 cycles is made for same compression ratio, same heat addition, constant maximum pressure and temperature, same heat rejection and net work output. The analysis will show which cycle is more efficient for a given set of operating conditions. So once again, the important variable factors which are used as the basis for the comparison of the cycles are your compression ratio, peak pressure, heat addition, heat rejection, and net work. Let's see the first case. Now in first case, we have the same compression ratio and heat addition. So the compression ratio is the same and heat addition is the same. So RC is the same and Q in is the same. Now the Otto cycle, 1 to, in this diagram, PV diagram, 1 to 2, 2 to 3, 3 to 4, and 4 to 1 is your Otto cycle. Now in diesel cycle, it's 1 to 2, 2 to 3 bar, 3 bar to 4 bar, 4 bar to 1 is your diesel cycle. And dual cycle is 1 to 2, 2 to 2 bar, 2 bar to 3 double bar, 3 double bar to 4 double bar, and 1 are shown in PV and TS diagram same. So on TS diagram, now you have to remember the area under these lines, okay? Which area is more and which area is left. Now case 1, same compression ratio and heat addition. From the TS diagram, it can be seen that the area 5 to 3, 6, area 5 to 3, 6, this area is equal to area 5 to 3 bar 6 bar is equal to area 5 to 2 to 2 double bar 3 double bar 6 bar, as this area represents the heat input, which is the same for all the cycles. All the cycles starts from the same initial state point 1 and the air is compressed from state 1 to 2 as the compression ratio is the same. It is seen from the TS diagram from the same heat input, the heat rejection in the Otto cycle area 5, 1, 4, 6 is minimum and heat rejection in diesel cycle 5, 1, 4 bar, 6 bar is maximum. So consequently, Otto cycle has the highest work output and efficiency. So diesel cycle has the least efficiency and dual cycles having the efficiency between the two. Now, in second case, we have a same compression ratio and heat rejection. Okay, so process 4 to 1 is the same and RC is the same. So let's see. In this case, efficiency of Otto cycle is given by a figure which is shown in the here. No. Efficiency of Otto cycle is equal to 1 minus QR over QS, where the QS is the heat supplied in the Otto cycle and is equal to the area under the curve Q3 on the TS diagram. The efficiency of the diesel cycle is given by efficiency of diesel cycle is 1 minus QR over Q bar S, where Q bar S is heat supplied in the diesel cycle and is equal to the area under the curve 2, 3 bar on the TS diagram. From the TS diagram in figure, it is clear that QS is greater than QS bar. So heat supplied in the Otto cycle is more than that of the diesel cycle. Hence, it is evident from that the efficiency of the Otto cycle is greater than the efficiency of the diesel cycle for a given compression ratio and heat rejection. Now, in case 3, we have a same peak pressure, peak temperature, and heat rejection. So we have a same peak pressure, peak temperature, and heat rejection. Okay, now let's see. Both figures shows the Otto cycle 1, 2, 3, 4 and diesel cycle 1, 2 bar 3, 4 on PV and TS coordinates, where the peak pressure and the temperature and the amount of heat rejected are the same. Efficiency of Otto cycle is 1 minus QR over QS. The efficiency of diesel cycle is 1 minus QR over Q bar S. It is evident from the figure that QS is greater than Q bar S. Therefore, the diesel cycle efficiency is greater than the Otto cycle efficiency when both engines are built to withstand the same thermal and mechanical stresses. Now, the case 4, when we have same maximum pressure and same in heat input. So Q in is same in all the 3 processes. So for same maximum pressure and the heat input, the Otto cycle 1, 2, 3, 4, 1 and diesel cycle 1, 2 bar, 3 bar, 4 bar, 1 are shown on PV and TS diagram in figure A and B respectively. It is evident from the figure that the heat rejection for Otto cycle area 1564 on TS diagram is more than the heat rejection in the diesel cycle 156 bar 4 bar. Hence, diesel cycle is more efficient than Otto cycle for the condition of same maximum pressure and heat input. One can make a note that with these conditions, the diesel cycle has higher compression ratio than that of Otto cycle. One should also note that the cycle which is having higher efficiency allows maximum expansion. So the dual cycle efficiency lies in between these two. Now the last case, same maximum pressure and work output. So the efficiencies can be written as work done divided by heat supplied is equal to work done divided by work done plus heat rejected. Refer to the TS diagram in this figure. For same work output, the area 1, 2, 3, 4 work output of Otto cycle and area 1, 2 bar, 3 bar, 4 bar work output of diesel cycle are same. To achieve this, the entropy at point 3 should be greater than entropy at point 3 bar. It is clear that the heat rejection from the Otto cycle is more than that of the diesel cycle. Hence, for this condition, the diesel cycle is more efficient than the Otto cycle, and the efficiency of dual cycle lies in between these two cycles. So now to sum up the summary of all the 5 cases, when we have same compression ratio and heat addition, Otto cycle has the highest work output and efficiency. In second case, when we have same compression ratio and heat rejection, efficiency of Otto cycle is greater than the efficiency of diesel cycle. Case 3, when we have a same peak pressure, peak temperature, and heat rejection, the diesel cycle efficiency is greater than the Otto cycle efficiency when both engines are built to withstand the same thermal and mechanical stresses. Case 4, when we have a same maximum pressure and heat input, diesel cycle is more efficient than Otto cycle. Case 5, same maximum pressure and work output. So diesel cycle is more efficient than the Otto cycle. Now, up till now, we have studied the 4-stroke cycles in Otto cycle, dual cycle, and diesel cycle. Now, what about 2-stroke? Now, let's find out 2-stroke SI engine cycle. An air standard approximation to a typical 2-stroke SI engine. Now, we on the same see the figure. On the x-axis, we have a volume, and y-axis, we have a pressure. We have a TDC, BDC, and we have a P0 atmospheric pressure. So let's see what's happening inside process 1 to 2. At process 1, we have a maximum temperature and maximum pressure. So your power stroke starts from here. So isentropic power or expansion stroke, all ports or valves are closed. So from 1 to 2, we have a power stroke and all the valves or ports are closed. So temperature volume equations, pressure volume equation, and specific work equation. Now, process 2 to 3 is exhaust blow down. Exhaust ports open and intake port is closed. From process when the piston is reaches at point 2, it uncovers the exhaust ports. So 2 to 3 is exhaust blow down. Exhaust gases are leaving in this process from 2 to 3, and process 3 to 4 and 4 to 5 is intake and exhaust sequencing. Now, when your piston reached at point 3, it starts uncovering the inlet port. So fresh air fuel mixture is coming in up till point 4 when the piston reaches to BDC. If intake port is open, exhaust port is already open. So fresh air fuel mixture is coming in, exhaust gases are leaving the cylinder. Now the piston is at BDC. Now it's moving back towards TDC. So it is pushing the fresh air fuel mixture, and fresh air fuel mixture is heavier in weight. So, and exhaust gases are lighter. So the heavier weight is pushing the exhaust gases, which are lighter, to the exhaust manifold or exhaust. So we have an intake and exhaust sequencing. Exhaust port and intake ports are common. So 3 to 4 and 4 to 5 is your intake and exhaust sequencing. At this point, 5 intake port is closed. Now let's see what happens next. Intake air enters at an absolute pressure on the order of 140 to 180 kilopascal fills. So if you see this, this is P naught, the atmospheric pressure, but here the pressure is more. So air entering in the cylinder is above the atmospheric pressure. Remember this thing in two-stroke cycle. And sequence the cylinder. The sequencing is a process in which the air pushes out most of the remaining exhaust residue from the previous cycle through the open exhaust port into the exhaust system, which is at about 1 atmospheric pressure. The piston uncovers the intake port at point 3, reaches VDC at point 4, and reverse direction, and again closes the intake port at point 5. In some engine, fuel is mixed with the incoming air. In other engines, the fuel is injected later after the exhaust port is closed. Now, from process 5 to 6, exhaust sequencing. At point 5, intake port or intake valve is closed. Exhaust port is open. We have a now fresh air fuel mixture here, or fresh air and exhaust gases. So piston is moving from BDC to TDC. It is pulling out, or it is pushing the exhaust gases outside. So up till here, your exhaust port closes. So exhaust scavenges continue until the exhaust port is closed at this point. Okay. So at this point, at point 5, your intake port closed. At point 6, your exhaust port closed. So in process 6 to 7, we have isentropic compression. All ports are closed. From at this point, point 6 to 7, this is your isentropic compression. You have a compression stroke here. Piston is moving towards TDC and compressing the air fuel mixture or air in which is entrapped in this chamber space, and compression is taking place. In some engines, fuel is added very near early in the compression process. The spark plug is fired near the end of the process 6-7 somewhere here. Now process 7 to 1 is constant volume heat input combustion. All ports closed. So somewhere here, spark plug ignites and we get the ignition and the combustion, and we have a constant volume heat input in the combustion process. All ports are closed. So the Q in is equal to the mass of fuel, heating value of the fuel, combustion efficiency of the fuel is equal to mass of mixture CV T1 minus T7. So P1 is equal to Pmax and P7 T1 over T7. These are the equations. Many compression ignition engines, especially large ones, operates on two-stroke cycle. These cycles can be approximated by the air standard cycle shown in figure. This cycle is the same as the two-stroke SI cycle except for the fuel input and the combustion process. Instead of the adding fuel to the intake air or early in the compression process, fuel is added with the injector late in the compression process, the same as with the four-stroke cycle CI engine. Heat input or combustion can be approximated by a two-step dual process. Let's see two-stroke. Previously, we have studied two-stroke SI engine. Let's see two-stroke CI engine. So this is the difference here. We have a both constant volume heat input and constant pressure heat input. Now from process 7 to X, from this point to this point, we have a constant volume heat input, first part of the combustion. All ports are closed. So V7 is equal to Vx and V is equal to VTDC. So volume at top dead center. So the Q in is equal to mass of mixture CV Tx minus T7. Px is equal to Pmax, P7 Tx divided by T7. Now second part of the combustion, that is at constant pressure heat input, all ports are closed from this X to 1. It is similar to your dual cycle which we have studied in SI engine. Now P1 is equal to Px and Px is equal to Pmax. So work done is P1 V1 minus Vx. So the heat addition in this is Qx to 1, mass of mixture Cp. So here we have Cp. Previously we have Cv. Now T1 minus Tx. T1 is equal to Tmax. Now this comes to the end of this chapter here. Now we will solve example 3-1 from the book in our next lecture.